This prototype, in which the players move their pieces, may prove to be a breaking point for us. It may prove to just be too difficult. You can't do this in the normal game of Battleship. I wonder if our previous code will allow us to model a game of Battleship for n arbitrary players, where there is some statefulness based off of how many pieces that you have that are active, where we're even going to maybe implement a special or a separate criteria, like once you sink the carrier, then maybe what that means is you lose the game, where the pieces can also move. Well, I guess that is pretty straightforward for us. It would be really nice. Let me do the following. Let's actually model a couple more pieces here. So let's put in the carrier. Let's say the carrier is a real heavy hitter. So that's your fleet. And that's what instead of calling it all ships, I should have called it your pieces. I should have called it your fleet. See, the greatest names always come to you at the last minute, right? Okay, so let's say we get your carrier here. We'll hard code this for now. So we'll put this somewhere in the middle, 0, 2, or we'll put it 3, 3, 3, 4, 3, 5. Nope, that overlaps there, so I'm gonna have to put it going down maybe. 5, 3, 6, 3, and 7, 3. There we go. So now we have a carrier in play, and what we'll do is we'll change the winning condition to either you have active ships and the ship is in your active ships. And actually, I think yeah, it should be this. It should be just the carrier is in your active ships. So the moment you sink the carrier, you're done. And now you need to be able to move. Well, I think that's not too bad, because what you can do once per turn is you can rearrange your board. And I think that means the strategy has to change. But I think that just requires that we take this board class and we allow them to move something. And I guess you can move each one of your ships. So here, I should let you move your ship, and I guess you can only move your ship in order for this to be valid. I can't say you can move it to a particular position, because then you could move something that's not valid. You could jump spaces. So here, this should be the direction that you want to move your ship, and I guess this is going to be something like north, south, east, or west, because you can only move on that grid. So something like this. And this brings up a very big question. What data do we need to preserve in order to do the analysis that we need from this simulator? Do we need to know the state of the board at all points in time? If we do, should this thing be immutable? I actually think now that this board type probably should be immutable. Especially since we'll later want to be able to analyze why somebody won based off of the way in which they moved their ships, and based off of where what was hit, and based off of any intermediate state of the game. So what that means is everything that mutated now needs to no longer mutate. And going from mutable to immutable is always really tricky, because we got to find all those places. The data class does make it relatively easy to work with these immutable types, and the disintermediation of values makes it pretty easy, because what we'll do is we'll just pass around these rich Python objects, and as opposed to having just lots of accumulated value type strings and ints everywhere, we have these enums and these data classes and whatnot being passed around. And so we can make copies of them only where necessary. Here's what I mean. In the strike, this actually changes the state of the game for you. So these two it's just this line that changes the state of the game for you. So what we would say is your new state is equal to the original state And I can just do a copy of this thing, or here we can even do this. It's equal to your original state, and then for the entry that was ship, it was whatever the original states had for the ship, unioned with this particular hit. Something like that. So this should be what our new state is, and this means that each strike has to return both the result and the board. So here it's going to return itself because we don't need to make a copy if it's the case that nothing changed. So here we're going to replace the state with the new state and return that as well. And so here we also will need to make these pieces that we were otherwise just creating in the post init. We'll actually have to make these things real here. So we'll have to make these visible for the data class. So we'll say this is a dictionary. And we'll just set this to none initially. It's a little bit ugly, but I think that's good. And then down here where we look at the shot, this is the new board. So we'll have to say boards for the opponent is equal to that new board. And we'll have to do that after, actually this is the new board. It's here, and the result. So we'll have to set that, I guess we can set that pretty much immediately because we don't need the board anymore. Okay, and we got to figure out what went wrong. So board from random, can't assign to field layout. Let's see. Why not? Oh, because this is frozen, and so this is a little bit ugly. For the frozen data class, well, I can show you a little trick that we can do. So we don't have to mess around with that too much. We can make this a field. We can say, we can give this a default factory, like that, and then we can update this thing. Because remember, the immutability of these structures is really just assignment to attributes, not anything else. Now, the last thing we need to do is, we get a stop iteration. So that means, so why is that happening? A bunch of misses and then a stop iteration. So the stop iteration is going to be, okay. So now this is where it gets really tricky. What we had changed was we had set a new board for everybody. And the stop iteration suggests that the new board wasn't tracking the state correctly. So it means that there's some field that we're not keeping track of. So here we have the original state plus whatever the ship state was, the one that we hit. So that's good. So this should be fine, but it suggests that we have something that's staying alive a little bit too long. And this is the state is the only place. So that's interesting. And if we return self, that's fine because you missed. But that means that there's something that the stop iteration means that we ran out of places to fire at, which suggests that the opponent wasn't correctly tracking their state of where their board was changing over time. Because if we kept this as being mutable, and one thing that we might do when we try and introduce this immutability, which we probably should have done from the beginning, if we want to really debug this, let's do this. Let's return self every time, but we'll actually just do self.state equals new state. And we'll turn off the immutability, and we'll see if the bug, where that bug is in our logic, because adding in this immutability after the fact, always a pain. So there we go. So here, so that's good. So replacing our self with the new state to get a new, let's do this. Let's now replace our self with our state equals a new state. This should have no real impact. That fails. So it's on the replace, and the reason for that isn't going to be, the size doesn't change, the ships that we have don't change, the layout doesn't change over time. It's only the state structure that changes. And that is odd. So we got to see what's going on here. And we should be able to get an exact copy of ourselves with just that one field. And there's no other data that is being captured somewhere that, yeah, it's interesting. I wonder if we just replace ourselves with nothing set, if that works. Very interesting. Okay, so that means that this replace doesn't work the way we think it does. So let's take a look at what this does. And we can see, and we'll see what the before and the after looks like. And so we'll see what you look like before and after, and there's something here that we're not catching correctly. So that's very hard for us to eyeball. So what we'll do is we'll say self.layout equals new board.layout. Let's do, oh, do we have multiple copies of the board? No, we only have, yeah, that might be, no, and we only capture the board size here, so we don't do anything with the board, so the board size shouldn't change. And here, this is only used for the context of this one line, and this here is only used there. So you can see here we've run into something very bizarre, which is, we assumed mutability, we tried to add an immutability, and it just kind of gets really tricky. This gives us some intuition. Anytime we're going through this iteration process and we discover that something is really, really running us ragged, it's probably a good candidate for something for us to consider the next time we try something like this. So the next time I try my hand at implementing a board game, a game like Battleship, probably would be a pretty good idea for me to design for immutability from the start, because it just becomes really tricky. If you can spot the bug, if you can see the bug, we'd love to hear it. Share this with us on Twitter or in the comments in the chat. But with that said, I see we're just about at the time that we had. We'll have to leave it here. We got very, very close to this final version. You can imagine that the implementation of moving, pretty straightforward. You just update the layout and recompute what the different positions are and just shift things around. It'll be a little bit clumsy to do that with our initial structure because you'll have to change all 4 of these items. So we'd have to do that, it'll be a little bit tricky, and we'd have to, change the state, we'd have to change the layout, we'd have to change the ships. I guess only 3 of those items. But for the most part, we're not going to be able to get there until we can figure out how to preserve or how we can solve this immutability problem. And we can see a very clear indication of places where choices that we made ahead of time do make it difficult for us to continue to iterate.